So we ended the previous lecture by stating that the mechanical momentum and the canonical momentum are not necessarily the same, in particular if the potential is velocity dependent. So just a clarification concerning the different types of momentum. So we have a canonical momentum, we have a mechanical momentum. Which is the real momentum of the particle or the system? The real momentum is the mechanical momentum. This describes how the particle, in this case, moves. It's the velocity of the particle multiplied with the mass. So the canonical momentum is not always the real momentum of the particle. This is the mechanical content sort of the momentum, the kinetic energy. So having introduced the canonical momentum, we're going to introduce one more term. We're introducing something which is known as a cyclic coordinate. We'll give its definition here. A coordinate qi is cyclic if the Lagrangian L does not contain qi, which is equivalent to saying that the partial derivative of L with respect to qi is 0. And I put ignorable here, just as a way of perhaps remembering what cyclic means. So cyclic means that L is independent on qi. So we can ignore qi in a way. If this is the case, we have the following. So what I've done here is to write Lagrange's equation, the first term of it anyway, and then the second term is 0 if qi is cyclic, because the second term is dl dqi. And then I use the definition of the canonical momentum. This term inside the parenthesis is pi, the canonical momentum. Time derivative is pi dot, and then equals 0. So this is our first important result in this section. The canonical momentum pi will be a constant if qi is cyclic. So for our particle in an electromagnetic field, you can imagine that if phi and the vector potential A are independent on x, then the Lagrangian is also independent on x because the kinetic energy doesn't depend on x. It only depends on the velocity. So we have this for the kinetic energy. So if I now do a transformation of the spatial coordinate from x to x plus some constant, so I'm just changing the reference system. So I call this x tilde. Then we see that x tilde dot is still x dot. It's independent on which reference system or which orgo I use. So the kinetic energy is independent on x. So in this case, we have that the canonical momentum px, which is associated with the generalized coordinate x, is conserved. But the mechanical momentum is not conserved. It's this quantity, mx dot plus qax, which is conserved. So let's now try to put this framework into a more general context and try to say something about what kind of conservation laws do we get in relation to translational and rotational symmetries. So you can think of this as a conservation law. You have that px, the canonical momentum in x direction, is a constant, so it's a conserved quantity. And it's conserved because the Lagrangian is independent on x. So we have a symmetry here. If you do x goes to x plus some delta x, the Lagrangian is invariant, so it's a symmetry. Let's start off with translational symmetry. Translational is perhaps a bit of a funny word because it might remind you of translating between languages. But what it means in this context is movement, linear movement of the system between 2 points. So we can have We're considering a situation where we have a generalized coordinate qj, which is such that an increment in this generalized coordinate, dqj, corresponds to translating the entire system, moving the entire system in a direction n vector. So you can imagine we have a particle I here, which has a position vector ri. All the position vectors in the system will be depending on the generalized coordinates. So it's a function of qj. So if we now increment qj with dqj, so that the new position vector of particle I is ri of qj plus dqj, this should then correspond to moving the particle a distance dqj along a vector n here. So this is the physical interpretation of qj for our purpose. And this could be x, for instance. qj could be x in this case. So you have the position of particle I here. You increment x by dx, so you're moving the entire system in the x direction, for instance. Using the definition of the derivative, we then have the following for how Ri changes with Qj. This is just the definition of the derivative. And by reverting to this figure, we see that the derivative of Ri with respect to Qj is just the unit vector in which the system is translated. Let's make an assumption that we're dealing with a conservative system. So the potential depends only on position. The Lagrange equation can then be written like this. So this is a bit different from the usual form where we would have L here and 0 here. So what I've done is simply that I've taken the potential energy V, which is usually contained here, and moved it over to this side. So this is completely equivalent to Lagrange's equations. And in fact, I think we wrote Lagrange's equations in this form at some step in the derivation. So this is a generalized force, which in the special scenario of a conservative system can be transformed into the standard form of Lagrange's equations. Well, this term is 0, as we commented on earlier. So this is the equation of motion. The time derivative of the canonical momentum, where I've used this definition here, since the velocity is independent on, the potential is independent on velocity, so that Pj dot is simply equal to Qj. Let's now try to say something about what the generalized force is for our particular system. This is the fundamental definition of the generalized force. And this quantity we have with amazing insight already derived. So we obtain this. Since the unit vector is independent on the index I can just take it outside of the sum. And then Qj is the inner product between the unit vector in which the system is translated and the total force F in the system. F here is the sum over all I for Fi. Or put differently, you can say that Qj is the component of the total force along this unit vector n. So that was one part of the equation. That was the right-hand side. Let's now see what happens for the left-hand side. So I have just inserted an expression for t here and then derived. It should be dot here, shouldn't it? And then derived t with respect to q dot. We now make use of a property which we derived, or at least introduced, in the beginning of this course, namely that this relation holds. We didn't prove it, but it's proven in the compendium. So I'm substituting this into here. So we see that whereas Qj was the component of the total force along the unit vector n, we see that Pj is the component of the total momentum large P along the direction n. All right. So let's now see what is the consequence if Qj is cyclic. Then large Qj, the generalized force will be 0. Since the Lagrangian is independent on small Qj. And according to our equation of motion over here, which I've now erased, but we had Pj dot is equal to Qj. So if Qj is 0, then the time derivative of Pj has to be 0. So if we were to summarize this in terms of a symmetry and a belonging conservation law, we could say that if you have a symmetry which is such that the system is invariant when you translate it in the n vector direction, which would correspond to an increment in Qj, since Qj means translation in the n direction. If you have that symmetry, then you also have a conservation law, and the conservation law is that the component of the total momentum in the same direction is conserved. So what it means is that if you have a system with translational invariance, it looks exactly the same in a given direction, then momentum in that direction has to be conserved. And this is an important principle, for instance, when considering optics or scattering of particles in junctions. So say you have two regions in space. One region where you have 0 potential energy, and another region where you have a finite potential energy. Or alternatively, we could consider a scenario in optics where you would have two different refraction indices, two different media. It could be glass and air, for instance. Now, in this direction, we don't have translational invariance. The system looks different as we cross this barrier. But if we now consider this direction instead, and just consider two semi-infinite plates, so this is a very wide region, then we have translational invariance along this direction. So for this kind of system, we have that Kx are not k, sorry, p. The momentum in the x direction is not conserved, but the momentum in the y direction is conserved. And you can use this actually to derive something which is known as Snell's law, which relates the scattering angles in these two media. So this is a very important application of we have a translational symmetry and a corresponding conserved quantity. So this was for translation. Let's now have a look at rotational motion. And if we are to consider rotational motion, we now look at a generalized coordinate, qj, that is such that an increment in this coordinate corresponds to a rotation of the entire system around some axis n. So in the translational case, a change in qj meant translation of the system along a unit vector n. In this case, consider now generalized coordinate instead, which is such that if you increment it, it means rotation of the system. Can you think of any possible coordinate that satisfies this criteria? Mm-hmm.
Phi coordinate in cylindrical coordinates?
Right. So the angular coordinate, the polar angle, for instance, phi or theta or whatever you want to call it, if you increment this angle, it means that you are rotating the particle around some axis, z-axis in this case. Now, we can use exactly the same procedure as we did for the translational case up to a certain point. We will get exactly the same equation of motion when written like this. So to get this equation, we simply use that the kinetic energy is independent on the generalized coordinate qj. But in order to move forward, we have to now consider an actual geometry of the system to see what the generalized force is when this is the generalized force associated with a generalized coordinate which corresponds to rotation. So imagine we have a particle I here with position vector Ri, which depends on the generalized coordinate times Qj. We start here. Now increment Qj with dQj. It corresponds to the rotation of the system along some axis, and we choose this axis to be here, this one. This means that the particle now moves from this point to that point. So it changes its position vector with dRi. And imagine that the angle here is theta. So in this scenario, Qj corresponds to an increment in Qj corresponds to a rotation of the system, the particle in this case, along some axis n here. Well, let's start out with trying to say something about the magnitude of the changes here. So the magnitude of this change in the position vector would be given like this. Ri sine theta is this radius from the m-axis out to the particle, and then multiplied with dQj. So the partial derivative of Ri with respect to Qj would be equal to this. And we are computing this quantity because we know that we're going to need it for the generalized force. So that was the magnitude. Can we also say something about the direction? Well, we see that dRi is perpendicular to both Ri and n. And if you inspect this figure, you can convince yourselves that this is the correct expression. It gives the correct direction for the derivative of Ri with respect to Qj, and also the correct magnitude, since n is a unit vector. All right, so let's now insert this into the definition for the generalized force. I inserted this expression here, and then made use of the fact that the torque, which I have here referred to as large N, is given as R cross F. This is the definition of torque. And small m, the unit vector, or the rotation axis in this case, is independent on I, so I can take it outside of the summation and end up with the following. The generalized force, Qj, is the component of the total torque in the system along the n-axis. Just as for the case with translational motion, we have that Qj is the component of the total force along, along the direction small m. And let's now consider the left-hand side of the equation of motion, namely Pj. So we have where again I've used this identity for this term, that you can remove the dots both up and down. So using the same derivation, we get that Pj dot is the component of the total angular momentum along the n direction. Sorry, it should be Pj here. And again, we now consider the case of cyclic coordinate Qj. Which means the generalized force is 0. And if this is 0, then Pj, according to our equation of motion, which I've erased again, which is the component of L along the n direction, has to be conserved. So for our case of rotational motion, we now have that if Qj is a coordinate which corresponds to the rotation of the system around some axis n, and Qj is a cyclic coordinate, then the component of the angular momentum along this n-axis has to be conserved. So the symmetry is an invariance with respect to rotation around an axis n. And the corresponding conservation law is that you have a conserved component of the angular momentum along this rotation axis n. And based on this observation here, we can immediately say that if you have a spherical symmetrical system where the potential energy only depends on the magnitude of the position vector, then the total angular momentum has to be conserved because you have rotational invariance in every direction. I would like to make one comment about the dimension of the generalized force. Now, in the system where we considered translational motion, we saw that Qj was the component of the total force along the axis m. In this case, where we consider rotational motion, we see that large Qj, the generalized force, is a component of the total torque, the torque large M. So in one case, the generalized force is actually a force, but in this case, it's not a force. In this case, the so-called generalized force is actually a torque, and it has dimension Newton meters, since the torque is the cross product between position vector and force. So this can be useful to keep in mind that actually sometimes the generalized force does not have the dimension of a force. This is why we call it generalized. And to understand why the dimension of Qj is not force in this case, we have to consider what are the generalized coordinates which have been used to obtain Qj. In the system where we had translational motion, I used x as an example. That if you increment x along one direction, that's translational motion. X has dimension length. In this case, as you pointed out, rotational motion around one axis could be provided by phi or theta, some angle, which is dimensionless. So the dimension of the generalized coordinates in the two cases that we've considered is different. In one case, it had dimension length. In this case, the dimension of the generalized coordinate was 0. It was simply an angle. And as a result, the dimension of the generalized force will also be different. So in case you ever end up with a generalized force which does not have the correct dimension, force, for instance, don't be too alarmed. You could still have the correct result. In the next lecture, we'll have a look at a conservation law related to energy, but I think we'll end for now.